Given the thermodynamic equation, H2 gas plus bromine liquid goes to HBr gas, the delta H provided with this equation is negative 72.4 kilojoules per mole. Like I said, you can find these delta H's associated with lots of reactions. They're all out there. They're measured. Calculate the amount. Okay, so this is what we want. Calculate the amount of heat released. Okay, so this means negative, delta H. That's exothermic. So it means that the answers might not have any negatives. And as I see, it's just implied. So we do not have to use the negative in our calculations. When a kilogram of bromine liquid is consumed. So 1.00, we're going to make it up, how many significant figures, kilograms of bromine. Okay. So is this balanced? Yes. All right, so we've got to use this as a conversion factor. So let's do negative 72.4 kilojoules equals, we're talking about bromine here. It asks for bromine. So we're going to focus on bromine. We're going to say equals 1 mole of bromine. All right. So here we're going to kilograms. So now we're going to convert that 1 kilogram into 1,000 grams of bromine. And then I'm going to look at the periodic table and I'm going to see that bromine is 79.9. I'm going to multiply that by 2 and I get 159.8 grams of bromine for 1 mole of bromine. And now I can use this conversion factor for 1 mole of bromine, 72.4 kilojoules is released. And so 1 times 1,000 divided by 159.8 times 72.4. And I get 453.07 kilojoules. And I see that the answer is B. And let's check that to make sure the answer is in fact B. Yes. All right, let's try 5.32. You just hit it. That's what you do.
I don't know how to ask someone for a written.
5.3.2. Given the thermochemical equation, okay, so we've got copper 1 oxide, should be able to do that, folks, goes to 4 copper solid. This is definitely an oxidation reaction because we've got changes of oxidation state from a +1 to a 0 and a -2 to a 0. The delta H associated with this reaction is a positive 333.8 kilojoules per mole. This is an endothermic reaction, folks. Okay, it requires heat in on the reactant side. Calculate the mass of, so we want grams of copper. Okay, calculate the mass of copper produced when 4.47 times 10 to the 4 kilojoules of energy is consumed. Okay, so the question is the mass of copper. So we want to figure out the grams of copper. And this is our given. This is our starting point. Now let's go ahead and get our conversion factor. So our conversion factor is 333.8 kilojoules equals 4 moles of copper. So now we can start with our given, 1.47 times 10 to the 4th kilojoules, and we can go here, 333.8 kilojoules for 4 moles of copper, and then we want mass of copper. So how do we go from mole of copper to mass of copper? we look at the periodic table. So when I look for copper, 63.546 grams of copper. And now I can do 1.47 e to the fourth divided by 333.8 times 4 times 63.546. I get 11193.84 grams. And I look at my answer and I see, oh, it's in kilograms, so I got to convert this grams to kilograms, or 1,000 grams into 1 kilogram. So now I'm going to take my number and I'm going to divide by 1,000, and I get 11.19 kilograms. I see that I have 366, so do we have 11.2? We do, and A is the answer. Okay, so that's how you use your delta H in those equations. Now, let's talk about calimetry. So in calimetry, this is how we measure the calorimetry. This is how we measure the heat in our food. So if you ever read food labels, you see that. We need to talk about specific heat and heat capacity. So specific heat is basically the substance is the amount of heat. So the specific heat is inherent. It's characteristic of a substance. So water has a high specific heat. Let's see, what does water have? You have a table there, 5.2. You'll be using it a lot for these problems. Do we have specific heat of water on there? Yeah. So water liquid is 4.184 joules grams per degree Celsius. Please always write those units down. Okay, it will be the difference of getting it right or wrong. So what this means is this is the amount of heat. So this is the amount of Q, heat, that is required to increase the temperature by temperature of 1 gram of material by 1 degree Celsius. And you can see that. Here's GC. So 1 gram by 1 degree. And Q is J. Q is J's, joules. So the amount of heat energy required to increase the temperature of 1 gram of material by 1 degree C. And you see water has a high number. Let's look at low numbers. Do you see what's the lowest number on there? Well, one of the lowest numbers is copper. Now, do you know anything about copper wire? What about copper on the bottom of a pan? Does it heat up quickly compared to the water? Yes, okay. And it's because it has a lower specific heat. So for 1 gram of copper to increase the temperature by 1 degree Celsius, it only requires 0.685 joules of energy, whereas water requires 4.184 joules of energy. So that is a little bit about specific heat. Heat capacity is, so specific heat is S. Okay, so specific heat is known as S. Heat capacity is C. So heat capacity. These are your formulas that you have to have memorized. Heat capacity is the amount of heat, so the amount of Q, joules, right, required to raise the temperature of an object. So the temperature of an object by 1 degree. So Q, the heat, you have two formulas. Specific heat times the mass times delta T. Because this could be different kinds of masses, right? And so you have the mass in there. No, or it could be Q equals C delta T. Now, what do you like about this? Not that it looks like cat, right? Well, C combines the mass times the specific heat into a state function. Okay, so that's the handiness of that equation. So you can take the heat capacity times the delta T. Delta T is the change of temperature, so T final minus T initial. T2 minus T1, because it's a state function, capital letter. Now, you use a thermometer, folks. Thermometer to measure the change of temperature. And this is how we relate change of temperature with substances to the amount of heat of something. So, one more thing about the change of temperature. What are the units here? Degrees Celsius. So, we're going to have to make sure our temperature is in degrees Celsius. And that's why when you look up a heat capacity, use those units and write those down, and they tell you want your mass, if you use M right here, to be in grams. You want delta T to be in degrees Celsius because it's in your given heat capacities. So you don't have to memorize anything, you just look at those. Now, what are we going to do with the calimetry? In the past, I just have you do sample problems like 5.5. I will not ask you to do the difference between constant volume, calimetry, and but I do want you to understand heat capacities. So let's just look at a few types of questions I will ask on this. So let's look at 5.4.2. 1 gram a sample of aluminum, iron, and gold are all heated from 40 degrees Celsius to 75 degrees Celsius. Arrange the metals in order of increasing amount of heat absorbed in the process. Okay, so now we're looking at heat capacities. Okay, so you need to understand what the heat capacity number means. So let's go to your table, 5.2 table, and let's write the heat capacities. I don't expect you to memorize these. So aluminum solid is 0.900 joules grams degrees Celsius. Iron is 0.444 joules grams degrees Celsius. And gold is 0.129 joules grams degrees Celsius. And so the question asks you to order the amount of heat absorbed in the process. So when you think about that, so the larger number is going to absorb and hold on to the most heat. Okay, so I always kind of think about water. Water has a 4.184, okay, joules per gram Celsius. You think of a bath of water or ocean, once you heat that water up, it can hold that temperature. And so aluminum has a higher, 4 is a big one, the solvent of life. So that's that number can hold and absorb a lot of heat. And so the smaller number is gold, and so that will be the least. And so the answer is D, where aluminum is greater than iron, which is greater than gold. So I want you to be able to think about what that specific heat means and the heat capacities, and then use it for heat transfer, like what we just did with the equation. Okay. Like I said, we're not going to do the calorimeter problems. Let's go to Yeah, so we're not going to do those. Let me look here in the back to see if I can find another example problems of something that you would need to be able to work with this equation. Okay, another example is, so your conceptual problems number 5.35. So a 6.22 kilogram piece of copper metal is heated from 20.5 degrees Celsius, so that's your initial temperature, to 324.3 degrees Celsius, that's your final. Calculate the heat absorbed in joules, kilojoules, by the metal. And so I need you to be able to recognize that this is the Q equals specific heat, delta T, times the mass. And your temperature, delta T, is T final minus T initial. I need you to be able to write your equations like this. And then you plug and chug. The delta T here, the final is 324.3 degrees Celsius minus the 20.5 degrees Celsius. And so you go ahead and find out your delta T here, 324.3 minus 20.5. So your delta T is 303.8 degrees Celsius. And then they give you the mass. Now, keep in mind, it needs to be in grams, okay? It's asking you for the heat, and it tells you copper. So you don't have to memorize those. Those will be provided in the question, the specific heats. But when you're doing your homework, I expect you to be able to go to your tables and use your book. So when I look up copper solid, 0.385 joules per gram per degree Celsius, that's going to be S. Okay, so Q equals the mass. I need to convert that. You see how that's grams? So I need to convert 6.22 kilograms. And for 1 kilogram, we get 1,000 grams. So now I can do 6.22 times 1,000. I get 220 grams. So now I can put that in for mass. 6,220 grams times specific heat 0.385. I expect you to use your units. And then delta T is 303.8 degrees Celsius. And so what happens here is then you can multiply 6,220 times 0.385 times 303.8. And so you get 7275096, and the grams cancel out, degrees Celsius cancel out, and that's joules. And it asks you for the amount of heat in kilojoules. So then we want to convert 1,000 joules for 1 kilojoule, not kilogram. And so I'll take that number and then I'll divide by 1,000. And these numbers are usually so big that we put them in scientific notation. So 12 kilojoules. And so that would be an example of how I want you to be able to apply this formula, okay, for the exam. And you do have a few other problems there. All right, so like I said, you can take out the Calimetry problems. If you do have problems, however, on your homework, you can use your book and you can figure out how to solve those. But like I said, you're not going to see those on your quizzes, and you're not going to see those on your exam assessments. So I'm not going to take the class time to go over them. Okay. The last topic in this chapter is Hess's law. And so in Hess's law, basically, the delta H of a reaction is independent of path. So what we can do is we can take lots of different reactions. So you're going to, when you apply Hess's law, you see lots of different reactions, and you can arrange them to give you the reaction you need. And sometimes you're going to multiply by a number, and then for your delta H that's associated with that reaction, you need to multiply that also by that number. Sometimes you're going to switch the reaction around, and then you'll need to change the sign for your delta H. Okay, and then you can total all these reactions up just like you can total up your delta H's, and you can come up with a new delta H for a specific reaction. And so because enthalpy is a state function, the change in enthalpy that occurs when reactions are converted to products in a reaction is the same whether the reaction takes place in one step or a series of steps. And so that's why we can do this. So let's just go ahead and look at checkpoint 5.51. So 5.51, given the following information. So you see a series of reactions here? So when you're given a series of reactions, you need to be thinking, oh, Hess's law. Okay, and you got to make sure you keep the states of matter and the delta H's all correct. This is kilojoule per mole. And then the next equation is 3 oxygens go to 2 ozones. That's ozone. And that delta H is a positive 284.6. Ozone is what is being depleted. Okay, now this is the question. What is the delta H for 3 hydrogen gas molecules and 1 ozone gas to go to 3 water gas molecules? So we got to rearrange these problems, these two, to give us this one. Okay, so we have to rearrange these. So what I do is I go to this first and I say, where can I find hydrogen gas? Okay, so I found hydrogen gas. And then I say, okay, so I just do this one first. Is the hydrogen gas on the reactant side or the product side? Because they need to be on the same side. They're both on the reactant side. Okay, so both. So I don't have to rearrange it. Okay, so that's the first thing I do. But then I also recognize that is the coefficient correct? Correct. Well, this is a 3 and that's a 2. So that is a problem. So how do I get the 2 to look like a 3? So I have to divide by 2 and multiply by 3. So I have to take this and divide by 2 and multiply it by 3. Does that work out? So what's 3 times 2 divided by 2? 3. So I'm going to multiply everything by 3 halves. Okay, and that means I've got to take this and multiply it by 3 halves. And so when I do that, I'm going to rewrite this equation. Okay, so when I do that, that gives me 3 hydrogen gas plus 3 halves oxygen gas goes to, okay, we have 3 times 2 divided by 2. So we have 3 water gas molecules. And then my delta H now associated with this is a negative 483.6 times 3 divided by 2. So now it's negative 725.4 kilojoules per mole. So I did that for each one of them. All right, so now am I happy? Do these match? These match. Okay, so now I can go on to the next one. So now I'm going to go on to ozone. I'm going to look for ozone. And I'm going to do something else. I'm going to scratch out this. Okay, so I'm not going to look at this anymore because I rewrote it. So I'm going to look here. Okay, so now I'm, like I said, I'm going to ozone. And do I see this anywhere? I do. I see it over here. Okay, so is it on the correct side of the equation, of the reaction? No. Okay, now another thing, you don't manipulate this. This is what you want. So don't touch this. You just manipulate these two equations and the delta H's. So what if I switch it? That's the first thing I want to do. So I'm going to switch this and I'm going to write 2 ozone gas, and we're going to say goes to 3 oxygen gas. And then I've got to switch the delta H now to a negative 284.6 kilojoules per mole. Okay, so now I'm going to scratch that out. So now it's on the correct side. Okay, so now I have the ozone on the correct side, but does it have the correct coefficient? Correct coefficient? No. So how do I make this look like that? Okay, so I can divide everything by 2, right? Divide by 2, divide by 2, divide by 2. So I'm going to rewrite this down below here. So when I take 2 divided by 2, that gives me ozone gas, and that goes to 3/2 oxygen gas, and my delta H now is a negative 284.6 divided by 2, which is negative 142.3 kilojoules per mole. All right, now I'm going to scratch that out because I rewrote it here, and I will hold on to that like that. All right, now let's look. Does this match this? Yes. Now we can scratch out anything that is on opposite sides, kind of like what we did with spectators. So we have 3/2 oxygen gas, we have 3/2 oxygen gas. Guess what, folks? These cancel out because they're on opposite sides of the equation. And then we're left with 3 waters. And you see you're left with 3 waters, and it's on the correct side of the equation and has the correct coefficient. So in Hess's law, we can total these two reactions up now. So if we total this up, we would see we have 3 hydrogen gas plus ozone gas. Okay, we scratched out those. Goes to 3 water gas molecules. And since we total that up, we total this up. So our delta H would be negative 725.4 kilojoules per mole plus a negative 142.3 kilojoules per mole. And so the delta H for this reaction would be, get my calculator out, negative 725.4 plus negative 142.3. Negative 867.7 kilojoules per mole. Now, is that what it was asking? What's the delta H? That is the answer. And let's look. We see negative 867.7 is C. I will check my answer just because that's a lot of stuff, isn't it? So 551 C, and C is correct. Okay, so you see how you just take your equation and you work with it. Okay, You can practice that with 5.52, and I think you'll be fine on that. Okay, so that's one way to come up with the delta H for a reaction. The next way is the final section of this chapter, and it's called the standard enthalpies of formation. So another way you can come up with a delta H for a reaction is using the standard enthalpies of formation. And so here you have a equation. So what is this? You'll see this is written delta H formation with the thing here, okay, that little superscript. And this is defined as the heat change that results when 1 mole of compound is formed. That's the F, formed from constituent elements in their standard state. Standard state is where you find them at like 1 atmosphere and room temperature. Okay, so by common agreement, all geographical heights and depths are expressed relative to sea level. So that's your standard state. And so you can look at Appendix 2 in your book, and you'll see that it lists standard enthalpies of formation for lots of elements and compounds. And make sure that you look at, so the delta H of formation of oxygen equals 0, but the delta H of formation of ozone is not 0. The delta H of formation of just plain oxygen is also not 0. So same thing with graphite. So the different allotropes of carbon. So you got to pay attention to the state of the element or the compound. Okay, so what's your equation? This is the equation you have to memorize. Delta H of reaction, because that's what we care about, at the standard states. That's what that superscript means. You can add all of these up, okay? This is actually, you'll find this is easier than what you just did to come up with delta H. So I'm doing this, but then I got to give you your equation. I should have probably given you your equation first, but doesn't matter. Okay. Okay, so what is this? This is an equation. So if you're given A plus B, and this goes to C plus D. So this is your starting material, or we call it reactants, and these are your products. The little numbers here are your coefficients. So if you look at here, you see that the C, and these are the numbers you look up in the appendix. This is your coefficient in your balanced equation, okay? And here you have, this is your products. So this is products. It's because delta H is a state function, so products minus reactants. And so you can sum up all of these. Delta H is a formation in your reactants and also in your products. And so this is a sum. So do you see that this is a plus? This is a sum. So you add them all up on the product side, and you add them all up on the reactant side. And you do products minus reactants of your delta H. And that can give you your delta H of a reaction. And so another way you're going to see this written is the following. Delta H of reaction is the sum of all of the delta H of formation of products So you can sum all those up, minus the sum of all the delta H's of formation of your reactants. And that's your equation that you have to apply. So let's look at how to do that. I am going to do the other one's asked for the delta H. Let's do 5.63. Okay, so let's apply this standard enthalpies of formation equation. So once again, you'll want to always write your equation, delta H, formation of reaction, and that we're going to sum the delta H of formation of products minus the delta H of formation of reactants. And once again, this is the standard enthalpy of reaction. You can find this Appendix 2. It's the first column. There's lots of data that you might need in general chemistry in those appendix. And I want you to note that when you have compounds in their elemental state at the room temperature and 25 degrees Celsius, that's standard state. So 25 degrees Celsius, 1 atmosphere. These measurements are made, and for any element that's in its natural form would be 0. And you can look these up as well. So, but if it's not given to you, then you can see that it's 0. So let's work 5.6.1, and our reaction is H2 gas plus fluorine gas goes to 2HF gas. And so if you go to the Appendix 2 in your book, which is at the back, you'll see that they're alphabetical order. And so what we want to do is the delta H of reaction, and we have 2 times HF, okay, in the gas, minus, and then we have the sum of hydrogen gas and fluorine gas. Now these are in their elemental state, so you can look those up and you'll see that those are 0 kilojoules per mole, that delta H of formation, and you can look that up and you can see that. I'm looking at it right now. Hydrogen and fluorine gas are 0. Now HF, though, is a compound, and it's not going to be that case. So let's look up HF. I see that HF is negative 271.6 kilojoules per mole. And so you have the 2 here, so you got to multiply it by 2. And then this is minus 0. And so when you do the math on that, that should come out to be delta H of reaction equals negative 543.2 kilojoules per mole. And you can also do this with 5.62 as well. Okay, so 5.63, you look at the ones that which of the following delta H values is a delta H of formation value. So you can do the problem, your hydrogen gas and bromine liquid, you look those up and those are going to be 0. So you can see those answers there. Anyway, I'm going to let you do the 5.62 problem, and like I said, I would make sure I had my key equations on page 217. So 217, I would make sure I have my key equations, and when I look at all those equations, the only ones that we're not really going to use, because we're not going to do the Calimetry problems, 5.16 and 5.17. So you can, for our exams, you can omit the calorimetry problems. But and I'm not going to ask you to calculate EK equals 1/2 mass U squared, and I'm not going to ask you to do the proportion Q1, Q2 over D, even though I think that's important. It's just not something that I'm going to ask questions about.